Now you will notice that I have generalized the discussion. So there are quite a few approaches that can be considered to be examples of these approaches, but we are looking at them in general. So basically we partition the system into a number of layers. Basically such that layer I can be exercised using only layer 0, layer 1 up to layer L sub I minus 1. In other words, so basically our approach is that here's a sequence. So first you test layer L0, the core layer, or you assume that if you cannot test it, just assume that it is good. And then using L0, you test L1, and using L0 and L1, you test layer L2, and using the earlier layers, you test L3 and so on. And so basically, idea is that you can exercise L3 using only L0, L1, and L2. And let us assume that when testing L0, L1, and L2, if you did not encounter any faults, and during testing of L3 you encounter some problems, then you will know that the problem lies there in L3. And then you can try to isolate the problem. And the question is, how do you come up with the layers? How do you identify the layers? And okay, before I continue, here let's see. Am I talking about hardware or software? I was thinking of hardware, but actually it applies to software also. Incremental testing is actually very common in software. As you are building your software, and in software it is actually easier. You build some core functionality, test it, make sure it works, and then add something to it, and make sure that it works. Then add another component to it, and keep on adding, and keep on doing your integration testing to make sure that what you have added works, and that is a common approach. In software testing. In hardware, how do you identify the layers? And that can be hard because it is not that easy to separate things. For example, if you have a processor, how do you divide the processor into layers? Now sometimes you may have to disable feedback during testing. In order to satisfy your assumptions of layering, especially the top assumption. And you may have to make some assumptions. Sometimes something doesn't quite satisfy your rigorous expectation. You may just have to maybe assume that it is reasonable, kind of make an approximation. Now you can construct proofs of a complete coverage. So when people did some early work on testing microprocessors, they actually constructed proofs that if you will come up with a fault model for each component, and here's the fault model for the whole microprocessor, and if you will do this, then with the assumptions involved, you will actually obtain a complete coverage. And so this can be constructed. Now, whenever we say proof, that actually means that you have to make some simplifying assumptions, otherwise it is actually too complex. Now, one advantage of incremental testing is that you can do fault isolation. With incremental testing, you can do fault isolation because you have exercised a part of it already and you know that is good. So whatever you have added new, that is where you are likely to have the fault. So you can do fault isolation. Now if your objective is fault detection and not fault isolation, you can argue that a reverse approach would actually be better. If you want to detect a fault quickly, and if that's your only objective, you don't want to do any fault isolation, then you should probably start at the highest layer. You should test the whole thing at the same time, and that way you are more likely to detect the fault sooner. But if you want to do fault isolation, incremental testing is a good way. Another name for incremental testing is, they call it start small testing. Now, here's an example of incremental testing. You have let us say, a microprocessor-based system, basically your PC, let us say. Then you could come up with this sequence. So that's an example. A microprocessor-based system. Actually, these days, every single thing, almost everything is a microprocessor-based system. The microwave oven is a microprocessor-based system. Your car is a microprocessor-based system. Everything is. So, so what you could do, you could start with a self-test for the processor. Processor should somehow test itself. And it should first test basic instructions. And if they work okay, check out all the addressing modes. And then check out more complex instructions. And somehow, if that all works correctly, then the processor okay, and then test the memory. You do the memory testing and you test the buses using the processor. And once you have tested the memory system and buses, then you can go outside. You can test I/O ports. You can go ahead and test your I/O devices. Theoretically, things like hard disk, optical disk drive, they are outside devices because they are outside of the domain that the processor can address directly. And then test peripheral devices. test software integrity. So this is an example of your incremental testing. And incidentally, in the slides, you will find a couple of rather well-known papers that use this approach. There was a famous paper in 1984 by Ibrahim and Abraham on functional testing of microprocessors. So that you will find that in the notes here. 1984. Let's say, do you have access to IEEE going back to 1984? Oh yeah, this is IEEE transactions on computers. So I think you should have access to, how far back does the IEEE Explorer go back?
82.
82?
Early 80s.
Okay, so I think you should be able to find it if you want. So that is our discussion on testing of sequential circuits. And in fact, many of the things that I had mentioned, they apply to testing of sequential systems in general. So many of these ideas are applicable to software as well. And we are ready to go into the next topic. Okay, so that is the end of our discussion on testing. Actually not, maybe we want to come back. So far we have considered only the deterministic approaches to testing. Now we have not seen some of the probabilistic aspects. So we have not talked about random testing, which is actually quite important. And I guess that is one main thing that we probably want to talk about sometime. And hopefully we will get some time and we will come back to random testing. But before we look at probabilistic aspects of testing, it is time for us to look at probabilistic methods. And now what we are going to be doing from now on, we are going to be in a different frame of mind. So right now we were saying that you do this, and if everything is okay, you're definitely going to see this. So our perspective was deterministic. There was no conditional thing that maybe this will happen. Actually, I did say that occasionally, didn't I? So actually, the truth is that you can never go very far from a probabilistic perspective. So, so let us then start looking at probabilistic methods. And this is a quick overview. Okay, so you have all taken courses in probability statistics or something like that. How long ago was that? So when did you take your...
I took application of random process a year back.
Oh, okay, so you have done that. So did you take the same course? No. So you have taken something different?
Not really.
So you haven't done anything in theory of probability and things like that?
Just random process.
Oh, okay.
Class, not theory of probability at all.
Oh, did you take that here?
No, it was overseas.
Oh, okay. How about you?
I took a probability class
Oh, okay.
last year.
Okay, so that's good. So yeah, it's good that you have taken it last year, so you still remember it. So, many of the things that I will mention here are kind of well-known things. And the reason I include that here is that I want to kind of refresh